Thank you. First, I'd like to thank the organizers for inviting me. It's a great pleasure to be in Taiwan for the first time. I think it's okay here, right? These two talks I will give is about holography and the random tensor network. So since this is not a conference like only for holography, so I think it will be good to give some more overview. So yeah, so the outline of my talks will be I will first give some motivation, which includes basically a brief overview of holographic duality and why we want tensor network. And then I will explain tensor networks and then focus on the random tensor networks. So for the random tensor networks, I will discuss some different properties of it. There are basically two aspects. One is one is about properties of a fixed geometry. As we will see in the discussion, the whole thing is about how to relate geometry to space. So when we focus on fixed geometry, we can talk about their properties. And then the second part, I want to spend some time on this new work that we are doing with my student Xiao-Liang and our collaborator Yu, where we talk about how to consider quantum superpositions of different geometries. Okay, so I will start by the motivation. So the motivation of this work is, of course, to understand holographic duality. And holographic duality was proposed in 1997 for Monsina. In summary, it's a duality between two systems that look very different. One is a gravitational system. In say d+1 dimension. So usually you think that as a bulk, like some geometry with a boundary and with a symptotic boundary, and then it has d+1 dimensions. Let's say, and then the other side of the duality is a quantum field theory. So from our purpose, we can just consider this as a quantum many-body system. So it doesn't even have to be a field theory that's continuous. So for me, it doesn't have to be like that. So, but it's just we understand this side at least formally. We understand this side better than that because we know that this is a quantum many-body system. It has a Hilbert space and so on. And so that's something that we know less. So in other words, this is just a quantum many-body system, and this is in d dimensions. And the duality originally was proposed, well, it was from the string theory. And then when you talk about the duality, the thing that people studied first are like partition functions and correlation functions. So you have partition functions of this theory, of the gravity theory, and that's equal to the partition function of the quantum field theory. And in particular, if this geometry is ADS space, then this side has the symmetry of the conformal field theory. So originally, this is called ADS CFT. But I want to emphasize that that's not, you don't have to restrict yourself to ADS and CFT. It's more more generally the correspondence between field series and geometries. ADS is a special case. Well, but usually you have a symptotic ADS near the boundary. So, so you have relation between partition function. So therefore, you have relations between coordinate functions. Like if you have operators here and you take them to near the boundary, then that should reproduce coordinate functions on the boundary system. And so you have correlation functions. So you take x, y goes to the boundary. Then there is a later part of the story which is more related, more deeply related to why tensor networks play a role in this field, which is there was this real-time dynamic formula that relates geometry with quantum entanglement. So that's not in the earliest works here. But so that sort of tells you more directly why do I have a geometry here? What's the meaning of the geometry? Instead of just calculating coordinate function on it, you directly calculate, say, the entanglement entropy of a boundary regime. And then the entropy of a boundary regime is proposed to be equal to the minimal surface area times some unit. So this is the minimal area surface bounding the region A in the bulk. So more generally, this surface has to satisfy this homologous condition. Yeah, homologous condition. Yeah. Confused by several words. So which means that this surface must enclose a bulk region together with the boundary region. Like if you have it doesn't have to be topological. It doesn't have to be homotopy equivalent to the boundary. Because you may have situations where like your box looks like this with a black hole, and then you have a regime like this big. Then the minimal surface is not this one, but something like disconnected to these two parts. So you can topologically change it, but you still you consider a regime that encloses a bulk that together with the boundary has to enclose a bulk regime. So yeah, well, means gamma A and A together is the boundary of a bulk regime. So this is Xiao-Liang. 2006. So this formula you can think as a generalization of Hawking, of this Bekenstein-Hawking entropy of a black hole. So in the black hole case, the area of a black hole is related by the same formula to the area of the black hole for L. It's related to the same formula to the entropy of the black hole. So here it's saying that actually if you look at a general regime and a minimal surface bounding the regime, it's also the relation between this area to entropy also holds. So this formula tells us that the meaning of the geometry of the bulk. If I start from the boundary, I view the boundary as my physical system. Then the bulk is like some kind of effective description. And so you can think the geometry, the whole geometry is like an order parameter that I use to describe my system. It's like a mean field order parameter. And the meaning of the order parameter is at least more manifest here. Like all these areas of different boundary regimes, they all have a meaning of entanglement entropy. And there are generalizations of the formula. I think that if you are in the earlier part of the workshop, you already heard from Kuhn's talk from holography, which means that you can use these assumptions you have needs. Okay, so so this is the key reason why tensor networks comes into play, because as we will explain later, it's very natural in tensor networks to have a relation between entanglement entropy and area. So before going to that, maybe I will mention a little more about generalization of this formula. So say what if say what if you consider the corrections, like you have a bulk field and that you have a bulk gravity field which gives you this background geometry. So you solve some Einstein equation, you get a background geometry, and then on top of that you can have quantum fluctuation. So you say, okay, what happens if I say create an EPR pair between gravitons, and then that will correspondingly, if you believe the duality is exact, like the two series are exactly 1-to-1 corresponding to each other, then when you do something in the bulk, that also change the boundary state. So in that case, you expect the boundary entanglement will be modified, and the generalization of this formula is you have this RT formula, and then you have the correction term, and the correction term is exactly the entanglement between these qubits in the bulk of this region. So this region enclosed by gamma A and A is called entanglement wedge, or in here I will call it entanglement wedge. More generally, it's called as the entanglement wedge is considered as a space-time region, but let's just look at space. So this is entanglement wedge. Then when you look at the generalization of the RT formula, the quantum corrections, where this term is much smaller than that when you have a small G Newton. That's always the limit we consider. So when we say larger limit, that means the limit where this coefficient is large. So this is the dominant contribution, and then you have the quantum correction. So so the quantum correction comes from just some qubits here entangled with qubits there. So you may have more complicated entanglement. But so any entanglement will contribute to this. So I'm mentioning this formula. This was pointed out by Faulkner. Look with Monsina. I was mentioning this formula because it gives you more intuition on what's happening here. I mean, like this formula not only tells me the area has a meaning, but it tells me like the correspondence between bulk and boundary. This regime plays a role. So like degree of freedom in this regime correspond to degree of freedom in that part of the boundary. So when you have some entanglement between this regime and the complement, it shows up in the entanglement of the boundary. If you have some EPR pairs here, it doesn't show up. It doesn't show up in the attribute of this regime. So more generally, there is what is called a local reconstruction. That when you consider an operator in the bulk, which may be that operator that creates some qubit, an operator in the bulk can be reconstructed to a boundary region A if this point is in the entanglement wedge. So this is a very important feature of holographic duality, which we will come back to later when we talk about the tensor networks. Because what happened is this makes this correspondence between bulk and boundary very had some very interesting properties which are related to quantum error corrections in quantum information. Yeah.
We compute the integral equation for d equal 1. What is corresponding quantity?
For d equal the boundary, you mean the boundary spatial dimension?
Or just d equal 1?
We need a spatial dimension, so
okay,
so it will be 1 plus 1.
So if we consider quantum mechanics, it's not okay to consider.
You mean 0 plus 1 boundary? That's a very good question, and we don't have this kind of incumbent attribute there. It will be very interesting. Yeah, you know there are these SYK model discussions, which is like a deal between 0 plus 1 and 1 plus 1. So indeed, what is the meaning of the geometry there? I think it's a very interesting question.
So it's not clear.
We don't know. Okay. Or at least, yeah, I don't think it's known. Yeah.
So what happens to the boundary when you have an entangled graviton in the ball?
Like this?
Yeah. What happens to the boundary?
It's some complicated thing here in common with something.
So it's no clear picture on the boundary.
Well,
For example,
it's not a. It's more or less clear because like if I have an ADS vacuum, and then I create a pair of graviton, then I know there is a construction by Hamilton et al. There you know in that case you know how to like map this operator to the boundary. So you know like there is say if you have an operator that creates something up here down here, then you do the other way. Then you know how to do it kind of like that. So you know what this operator that creates the particle corresponds to one boundary. But in general you don't know. In general you don't know the explicit form of the operator, but you know there should be a one-to-one correspondence. Like if you prove these kind of formulas, then the consequence is there is a one-to-one correspondence between states in here and the states on the boundary. So you start from the ground state, and then whatever operator you apply in the box, it should be mapped to the boundary with isometry. It means there is another operator on the boundary, which give you the same, which acts in the same way on the table.
So I want to ask one more question. So if we consider SYK model for D equal 1, then do you expect the two-dimensional box theory is some quantum field theory or topological graph? Because I always appreciate because ADS the box theory is just a classical. So
No, it's not just classical.
but I just need no. The leading order was I just consider the minimum surface.
It's in the large. Well, the interesting case is when it's in the large limit where it's.
So now if I also consider large limit for D equal 1, do we still expect that the leading order is just classical?
I thought that's true. I mean, the proposed dual of SYK model is some dilaton gravity, and there is a.
The two-dimensional gravity is just topological.
Yeah, so all the degree freedom are on the boundary actually, which means you don't really have fluctuations in the bulk. Do I understand? Correct?
So it's needle. So as I said, so non-trivial leading order is quantum.
No, I thought that means it's exactly completely classical on the bulk because like the equation of motions are exactly satisfied. But all the fluctuations are on the bulk. The bulk equation of motion becomes something like constant. But I don't know. Maybe we can talk about more of that.
So is this a minimal surface also fluctuating?
This minimal surface generally should be fluctuating.
Yeah.
So in this limit where I think this term is completely dominant, then it's fixed. But in general, if this coherence is finite, actually there was a proposal that you should be thinking of minimizing this whole thing rather than minimizing only this. So that means that when you think about this, it's back reacting to the geometry. Okay. So now maybe I will switch gears to the tensor networks. I want to start with the introduction of tensor networks. Maybe you have heard that in the earlier part, I'm not sure. So basically, okay. So why tensor networks? Before going to the details, what we want here in this duality story, there's a lot of evidence that the duality is true, but it's not like a macroscopic derivation. You can verify it in many ways. But so what we want is like it's sort of like a macroscopic framework. It's like if the duality is exactly true, then the mapping between the two series is like one-to-one. There's states to states. So instead of talking about coherent functions and entropy, we can talk about like the states in the two series are exactly one-to-one map and the operator. in other words, if you think of a Hilbert space kind of formalism, then you should have a mapping, one-to-one mapping between the states. That means you define a linear map, which is reversible and one-to-one unitary. So that's what we're looking for. And then then the idea of looking for such a map is basically to the leading order, different geometries here give you different states. Of course, for each geometry, there is still a lot of quantum fluctuation around it. But roughly speaking, the idea is geometry corresponds to states, and that's what we want to describe using kind of networks. Describing using geometry as a way to specify different quantum states and study whether we can define such a map. That's the network. So I would like to start thinking of a very physical way to construct the network states. So so let's think about a physical process that you have some machine that generates PR pairs. So you have some apparatus, so some of your experiment lab equipment. Then you emit some pairs of photons that are entangled. Okay, so that generates entanglement, but in a very simple form. And then you can consider many such pairs. So you have So you consider many such pairs, and then you send some of the photons to somebody and some photons to some other people. So let's say in this picture I have 4 people. Say Holden, Alice, Bob, and Charlie, and maybe David. So anyway, so that's following the convention. So you have the EPR pairs and you distribute them to different people. So they each have 1, and then David has 3. Okay, so now in this state, in the state of the whole system, there is entanglement between A, B, C, between R8, Bob, and Charlie to David, but there is no entanglement between them. So it's just these pairs has no relation to each other. There is no entanglement between A, B, C. Okay, so now this is the first step. And then you consider the second step, where David do a measurement. So David take these 3 photons and then do a measurement. And the output of the measurement is some pure state. So let's assume the measurement is complete, which means you measure some physical quantities that's a complete set, so that you get once you know the quantum numbers you measure, you get a pure state. And so you measure, and then you get some pure state, which we call VA, with some probability. So A labels different outputs, and then you get one of the outputs. So if what David do is completely isolated from these 3 people, these other 3 people, then the measurement doesn't change the state of ABC. But if you measure and then you tell the other 3 people the result, then you can think this as like a collapsed wave function. So you through some classical communication, you tell ABC that you measure and you get output A. Then what is the state of the system seen by ABC? Then the state of the system will become before this process, we get a state that's like some EPR pair between AD, BD, and CD. And then after the measurement, you get the state that's obtained by projecting the state to VA. You get other sectors, but then once you tell other people through the classical communication, then we are all in the same universe that we only see this one. So effectively, the wave function becomes this. And now that these three photons are projected to a pure state, then then D is out of the story. So then David now is not entangled with anyone because I got a pure state. So David is not entangled with anyone, but A, B, C are entangled. The other three people are entangled through this process. So after this measurement, you get basically you connected these three photons into some state, and as a consequence, the other three qubits that are not measured, they got an entanglement between each other, and this entanglement can be much more complicated than EPR pairs. So you can put an arbitrary state here, and that gives you some general three-party entanglement. And more generally, so this is the idea of tensor network. More generally, you can do this for multiple David. So you can have a network where you first pair EPR pairs across links, and then for each vertex, what I call bulk vertex, which means it's like an internal vertex in the Feynman diagram. Like all these bulk vertices, you do a measurement on some states, and you project all these to pure states. Then they are out of the pure space. They don't evolve in the entanglement anymore, but they induce some complicated entanglement between the remaining qubits. So the tensor network is just a way to create more complicated entangled states using this procedure from simple entangled states. And this procedure is exactly what this name means. This name of traps projected. So tensor networks are also called PAPs, and that's exactly this picture. So you have entangled pair states and you project. So in general, this was by Verstraete and Surratt. I think this name was given in 2004. So in general, when you have a network like this, you write down wave function like that, which is a projection on every vertex here, act on the EPR pairs on all the cross all the links. Any questions about this part? Okay, so you see this is a very general thing because I can use any graph and it can be local and local any dimension. And then and you start with this in some states with a simple entanglement, you get a more complicated many-body entangled state. So and the key reason why this tensor network is related, well, it looks promising that it's related to holography, is the geometry plays an important role in the network. So if you look at a network, for example, if I look at a network like this, by the way, when do I talk now?
Still half an hour.
1 hour, okay, good. So you have a network like this, which is the state of the 4 qubits. These other qubits are all projected out. Then let's call these 4 qubits A, B, C, D.